enter. Did I ever fix attendance so that Connor was just tardy and not absent? Yes. All right. Oops, I didn't do that. Okay. So, we want to know what happens to this graph as x approaches 2. Now, just because I would like to see it, I'm going to actually look at the graph here and see if I can kind of tell what's going on. So, from my graph, right here would be x equals 2. It looks like that line is stopping, but there's a chance that my graph, these graphs are sort of limited here. It looks like it stops at about -4 there. But some things you need to know about these graphs are that sometimes if you have asymptotes, they don't show very well. Sometimes you can have some weird things that look one way, but if you zoom in, it will look differently. Desmos gives you a much better graph, honestly. Desmos also has its limitations on graphing, but it's much better. So going by the graph here, I would go with maybe -4 if I had to take a guess, but that may not be very accurate. So the table helps us verify whatever is the case here. So what we're going to do is we need to think about the number line, and we're approaching 2 from the right-hand side. So what's a number bigger than 2? 3. Right, so let's type in, actually, first let's try 2. Let's just plug in 2. And a lot of times when you type in 2, actually, do you guys get negative infinity or do you get error? Undefined. Okay, I remember running into this last year, and I think usually, I thought it would give you undefined. This is actually a really good answer right here, but for negative infinity. But usually that does not show up. I think this clearly, is like an older calculator. So I think when they updated the operating systems, it did something different. So you guys are probably getting undefined. If you get undefined, you got to keep on going to figure out what's actually happening here. So, again, we don't care what happens right at, and you have to be careful because you don't care what happens right at 2. You care what happens as you approach 2, which usually if you plug it in, it's going to be the same number for a function, but not always. So, so if I plug in 3, I get 0. So I'm going to write down the table here just for, if I plug in 3, I get 0. So that was right here. What is a number that would be even closer to 2? Okay, so if I put 2.9, that'd be like here, right? So if I try 2.9, I would get negative 0.2107. Okay, give me something closer to 2. 2.01. So we're jumping. We're going real close, right? 2.01. Now I've got at 2.01, I've got negative 9.21. All right, I need something even closer. Okay, so 2.00001. Now sometimes you get a little out of the range the calculator can handle. So if we get something weird, we would back off and take some of these zeros. Let's see what happens. All right, we get negative 23. Sometimes you also might want to go over here and make sure you don't, sometimes you'll end up with like scientific notation on those. I'll see if I can make it do that. So we get negative 23.03. What would be even closer? More zeros, right? If we have 2.0000001. And now we're getting, so 2.0000001. Maybe that's how many I put. Negative 36.84. Okay, we could keep on going with this if we wanted. We could just put tons of zeros. Now, I might overstep the limit. Here, I have overstepped the limits of what the calculator can handle, and it's just giving me negative infinity. Your calculator might give you an undefined if you do too many zeros there. And it's not that that value is actually undefined. It's that the calculator, it got so close, like the number was so close to just being 2 that it couldn't handle it anymore. But if we look at what's happening here, these numbers just seem to be getting more and more and more negative, right? So we could infer that it is likely that this equals negative infinity, right? Now, it is possible that this would stop at negative 40, and negative 40 would be your limit. That's possible. Given what we know about natural logs and those having a vertical asymptote, that's not going to be the case. But it is possible that it stops at negative 40. We have not proven that this limit is negative infinity, but the evidence that we have supports it. And that's going to be the best you can say whenever you're doing numerical limits, because this doesn't guarantee that it's that case, but it supports that you've got that numerical limit. And again, when I looked at the graph, my picture didn't really show that. It looked like it stopped. Does yours look like it stops if you graph it as well? And it's just the limits of the calculator, because that graph is getting closer and closer and closer to the asymptote, and it gets so tiny and so close that it can't graph it anymore, right? Because it's limited on its pixels and what it can show you. So the graph can help you, but you don't want to go strictly by the graph because it will mislead you sometimes. All right, so let's try this one. What's great about these calculators is when you plug in your equations, into y equals, when you hit enter, it'll show it to you in like math notation instead of just being a long string of things. Now, the more updated 84s might have done that on some things, but all of the 89s show it to you like this. So always, once you get it typed in, look back here and make sure that it works. What is a little bit annoying about this is if you don't finish your parentheses, like if I leave off that last parentheses on the 84, that would have been fine. It would have just ignored it. On the 89, it gives you an error and tells you you're missing a parentheses. Have any of you had any coding classes? If you do coding, your parentheses can drive you crazy, especially when you start doing like commands inside of commands, because if you don't have your parentheses in the right place, your program's not going to work correctly. The 89 is, of course, not like as extensive as programming, but it gives you a taste of that. It can drive you crazy sometimes. Okay, let's go to our table. This time we're approaching infinity, so we just need numbers to get bigger, right? So like we start at 0, and then 10, and then 100, and then 1,000, and then put a bunch of zeros, right? What does it look like is happening here? It looks like my numbers are getting tinier and tinier and tinier and tinier. Over here, I even go into scientific notation, so this means that decimal's got to be moved back 6 places. So it's just getting closer and closer and closer and closer to 0. So we would say that this limit right here appears to equal 0. Right? That's what our table supports. Now, as we go along, we're going to learn other ways that we can prove that that is actually 0. But right now, we just have evidence that supports that it is 0. Now, first one, there we don't learn anything. That one is one that pretty much has to be done numerically. Algebraically, we're not going to have any methods for dealing with that natural log right there. Okay, so this one's not using the calculator. It just asks the question, which of the following statements is supported by the table below? Okay, so our first one says the limit as x approaches 2. So 2 in our graph would fall right here. Right, that's where 2 would be. The limit as x approaches 2 of f of x equals negative 4. Is that supported here? Are you sure? From both sides, because this is a limit from both sides. From the left side, so if I had a little negative right there, it would be supported, correct? Because from the left side, it does look like you're getting closer to negative 4. But from the right side, what does it look like you're getting closer to? Looks like it's positive 4. So, from both sides, this is not supported. It's possible, because this graph could go up to 3.92, and then it could go back down to negative 4. It's possible, but it's not likely. It's not supported by this table, right? There. All right, B, we've got the limit as x approaches 2 from the right of f of x equals negative 4. Is that supported? Okay, it is not. What does it look like we're going to? It looks like we're going to 4, not negative 4. So B is out. Okay, limit as x approaches negative 4 of f of x equals 2. Does our x approach negative 4 anywhere in this table? Now, it's certainly possible. It might happen. We don't know because we don't even have that piece of the graph we would need to make that assumption. But this does not support that claim, right? So all three of these so far are possible, but they're not supported by this. Oh my goodness, what have I done? I have messed this up bad on D. Now, the claim limit as x approaches 2 from the right equals 4. Does that look like it's supported from this graph? Okay, it looks like from the right, 4 is where we're going. So this needs to be my answer, but I have made a terrible, terrible, awful notation error here. Okay, what's wrong with the way I have written this? There's no f of x. This is what I call, you can write this down. You can draw this little man right here. This is what I'm going to draw on your paper if you do this. And I'm going to say naked limits. And this little man is appalled at the offensiveness of this naked limit that you've got right here on the page. Because a limit has to be of something. Right, see right here I've got f of x, I've got f of x, I've got f of x, or you might have the equation. But you can never have just a limit of nothing equals something, right? Because right now I've got nothing right here that I'm taking the limit of. So this is a naked limit, which I did not realize that I had on here. But I might leave as an error in these notes just because it's a good place to point out that you can't have naked limits. And you guys will do it. The offensiveness of the naked limits that I see on papers whenever I start grading stuff is awful, and I'm going to draw this little man right here that is shocked at what he's seeing because we can't do that. So really this should say limit as x approaches 2 from the right of f of x equals 4. And if it said that, D would be correct. That is supported by our evidence. It's also quite possible that this goes to positive infinity. That's That is a possibility that we have here. But it is possible that it goes to 4. We just don't know given the information, but it is supported. Okay? Questions? Watch out for those naked limits. That you guys had me last year in pre-calc, so you guys know, but same thing holds as it did last year. If you find a mistake on something that I have published, so not just like I'm writing something down and accidentally write it wrong in class, but like this would count because this was notes that I had already printed out for you guys. It has to be like a mathematical error, not just like a spelling error, grammar error, or a typo, unless the typo actually changes how you would do the problem, right? So, but this would count right here. If you catch something like that, and you are the first person to catch it, you can get an extra late worker bathroom pass for catching my errors there. So be on the lookout. There's probably plenty of opportunity because I mess things up a lot. Like, for example, I'm not going to give you credit for realizing that I have 2 example 3s in a row because I apparently have a hard time counting as well. And which of the following statements, that shouldn't say is, should just say must. Listen, guys, there's not much time for me to proofread any of this stuff that I'm doing here. I've got too many things to do. The quality of my work is questionable sometimes. All right, which of the following statements must be false according to the table below? All right, so limit as x approaches 0 of f of x does not exist. So let's find 0, of course, that would fall right here. That's where we're looking. Do we have a limit that does not exist? For sure. We can't say that it must be false. It is possible that it is false, but we can't say that. Limit as x approaches 0 of f of x equals negative 5.5. Does that have to be false? No. In fact, that one looks like it's true. It appears true, right? It appears true, so that's not going to be our answer. Limit as x approaches negative 5.5 of f of x equals 0. Does that one look like it's false? I would say it looks like it's false. But I specifically put this word right here for a reason just to emphasize something here. Does that have to be false? It does not have to be false because all we're given is numbers here. This could take a turn back up to 0. That is possible. Unlikely, but possible. So it does not have to be false. What about the limit as x approaches 0 from the right equals the limit as x approaches 0 from the left? So from the right side, we've got this negative 5.49 is the closest we get. And over here we got negative 0.49, negative 5.49. That also appears true, right? This looks like we're going to negative 5.5. It looks like those limits from both sides are the same. So this appears true. I put this question here specifically to emphasize to you that whenever you are doing numerical limits, whenever you see something like this, something must be false, then you're not really going to be able to prove that. So there's no answer for this. This was a trick question that I had thrown in here on purpose for you. So, so watch out for that. Now, if it said is not supported, your best answer for is not supported would be that C, it does not look like this is going to go back up to 0. It also doesn't necessarily look like it's going to be does not exist, but it is possible that that goes to negative infinity, even though it doesn't really look like that's what's happening. So I'd say the best answer would be C if it used language that was less stern there. So I'll just put that there for that. So we are going to do some AP Classroom problems right now.